Yeah.
Good evening, everyone. My name is Ainim Babazi Martina.
And my name is Namito Maria Leodeska.
Good evening. This is Rugamba Gloria.
I'm going to present our project on multimodal machine learning architecture for food supply optimization, mitigating the sectoral gap in demand forecasting. This is SWML17, and this is what we have for this deliverable. Gloria, I can change pages. For the introduction, this project we are working on is based on the demand and supply for food vendors in Makerere University. We have an issue of shortage and surplus, and we never have a middle ground for these vendors. So from the research we made, we were able to gather data and we were able to create a synthetic agent that could get us synthetic data sets that we can use for supply chain management to solve this problem.
For the problem statement, we have the domain problem statement and the computational problem statement. Now, for the domain problem statement, we realize that cafeterias and kiosks in Makerere tend to prepare so much food, which sometimes leads to problems like wastage, revenue instability, poor inventory management, and many other problems. Now, for the computational problem, as we were coming up with our multimodal food supply chain optimization system, we realized that there's a sim to real domain shift. And this is what we are trying to mitigate. It's what we are trying to solve. This came up as a result of using synthetic data sets because we were unable to get real data from the cafeterias and kiosks, because most of the food vendors don't really record their data, and some of them record, but the data was not enough for us to use for our models. Now, we were able to synthetically generate data sets that we used, and that caused the sim to real domain shift that we are trying to solve as we are coming up with our system.
Next, this project, first of all, it uses two data sets, and as the speaker before said, the two data sets were synthetically modeled. And what this means is that we had to generate our own data, though still as a team, we moved around a few cafeterias and kiosks in Makerere University, and we collected few data, which we then used to generate more data based on the information we collected. And we are able to see that the two data sets include a cafeteria production data set with the truck's daily portion. And then it has columns representing the wastage percentages within the university and revenue. Then the kiosk transaction data set. It's also a data set that represents the kiosks working within the university, and it captures daily temporal demand.
Our main objectives for this system, we have so many, but the main is to analyze the food demand patterns within Makerere University. We also have to identify the demand supply mismatches. We have to quantify waste and its financial impact, examine temporal purchasing behavior of students and staff, and propose a smart predictive supply chain system. All this is going to help both the vendors and the students, so that the students are able to get the food they want from the vendor they would like to get from, and they could get any food choice without going at a time and they say food is done. This would also help the vendors be able to produce the correct amount of food so that they do not waste food. And also it would help them produce enough food so that there is not a time when people ask for rice and rice is done. We can proceed.
Now, for the research contributions and output, our project contributes empirical evidence. Now, after carrying out our exploratory data analysis, we got visualizations that helped us to analyze the data, and we discovered a demand-supply mismatch within the university or the food system of the university. Then operational insight framework. This identifies the demand volatility. This means that demand is not static. Demand keeps changing depending on days of the week, the semester periods, and many other factors. Then also it contributes a smart supply chain management model design. This is what we are trying to work on. Then temporal demand characterization. This demonstrates strong hourly and weekday demand clustering. Then the research outputs, these are the outputs of our project. We got a cleaned and structured cafeteria dataset, as well as the kiosk transaction dataset. Then we got visualizations from our exploratory data analysis. Then from the visualizations, we got the demand supply mismatch analysis that I talked about earlier. Then we were able to quantify waste, and we got a smart supply chain system architecture and a blueprint for our ML forecasting models. Next.
So next on our project is we were able to obtain visualizations after carrying out exploratory data analysis. And the first one of the visualizations we achieved to get was a bar chart that shows the total proportion sold per each meal within the cafeteria dataset. So this bar chart, as you see, the blue represents prepared meals and the orange represents the sold, the proportions sold. So we are able to see that Rolex has the highest amount that is prepared and also the highest amount that is sold compared to Katogo that we see lagging behind with the least amount prepared and the least sold. Then our next diagram here, visualization, is a correlation matrix showing the amount of revenue obtained from each meal within a week. So how this visualization works is the darker, the maroon that we see shows a very high level of revenue generated from a specific meal. And we are able to see that rice and chicken tops the list with the highest revenue generated from it. Then the list are the ones that are pale orange as the color keeps on changing towards a lighter note. It means the revenue is also decreasing. So from our visualization, we are able to see that on Saturday and Sunday, revenue generated is less compared to the days during the week, because as we may see that most students are not within the campus.
Okay. For the next visualization, we have two. We have a time series of daily total revenue over time, and then we have one for revenue versus the waste cost by meal, and that's the scatter plot. So for the first visualization, our data comes from 2024 and 2025. And within the months, we have noticed that we have high revenue collected and low revenue collected depending on the month by these different cafeterias. During holidays, we have noticed that there is very little revenue collected by these cafeterias. But during semester periods, we have high revenue collected. As we can see that there's a spike during the end of these different semesters, and that means that's during exam period. So we have noticed that during exam period is the time revenue is collected the most throughout the semester. For the visualization of revenue and the waste cost, we are seeing a positive kind of gradient, because we see as a lot of revenue is collected from a certain meal type, a lot of waste cost is collected as well. The meal type that is getting the most revenue, as we have seen, is rice and chicken, but it's also the meal type that has the most food wasted. So that means that cafeterias are also wasting a lot of rice and chicken as they prepare and make lots of money from it as well. We have also noticed that Katogo, it seems Katogo is prepared less because we also have less waste cost, and we also generate the least revenue from it.
Now here we have a horizontal bar graph showing total gross profit by meal type. Now we can see that Rolex generates the highest revenue because it has the longest horizontal bar, and Katogo generates the least revenue because it has the shortest horizontal bar. And that the longer the bar, the higher the money, or the higher the revenue. Now on the right rather, we have a correlation heat map, and the color of the heat map indicates total usage, and on the y-axis we have the ingredients, and on the x-axis we have the days of the week. Now we can see that egg units have a deep blue color, which shows that from Monday to Friday, egg units are the most used ingredients. Then also on Saturday and Sunday, they are used, but not so much. Then we can also see that matoke is used mostly on Monday, and from Monday to Sunday. Then the rest of the ingredients have a very, very light blue color. That means that they are used, but not so much as egg units and the matoke. Because when it comes to eggs are served with different kinds of meals, and also matoke is served alone, and it can also be served with other kinds of foods like katogo. So the matoke units are obviously used in plating as the egg units. Next.
So next we have a bar chart. On our left, we have a bar chart that shows the total revenue generated by each item sold in the kiosks. So each item is represented by its own color. And this bar chart generally shows us that Rolex is the highly sold out item within the kiosks in the university. And next we have the samosas. And then this bar chart also shows how much revenue is obtained by each item, and we see Rolex being sold out the most generates the highest revenue. Then the rest of the items come in, followed by samosa, and lastly mandazi. Then on our right, we have a stacked bar chart that shows total revenue generated by each kiosk location. And it's able to also show us the different academic periods. And we are able to see that the dark blue represents semester 1 exams. Then green shows the semester 1 teaching period, which is the period just before the opening date, and the period from starting from the opening time, the semester, up to exam period. Then we have purple that represents semester 2 exams. The pink showing the teaching period of semester 2. And then the yellow that shows the break between semester break, the break between the two semesters, and then Christmas break. So this bar chart generally shows us how the different kiosks within the university are able to generate revenue based on the different time seasons.
So from the visualizations and the exploratory data analysis that we have done, the results that we have come across is we have noticed that there is a demand supply mismatch. The food that is prepared is not equal to the food that is asked for, and that's why there is wastage. We also have waste distribution, which I've talked about earlier. We have different meals that are being wasted, and this is going to reduce the gross profit of the vendor. We have revenue patterns where there are fluctuations within the days of the week. You'll find Sunday is generating a way lower revenue than Friday. We also have temporary demand behavior where we have noticed that there is a difference. We have temporary transactions during the week. There's a difference in transactions during the week. We can tell through these hourly peaks, and that means that vendors have to take keen notice of what time to prepare a large sum of meals and the time to prepare less. So the cafeterias will have to improve on that. We also have ingredient usage patterns where the consumption is varying. So this is going to help in procurement in a case that during the week, if we are aware that Rolexes are mostly sold on Friday, we have to make sure that on Friday there's a large amount of eggs to be used. There's a large amount of wheat flour to be used, and so this is going to help in procurement.
Now, we have come to our conclusion, and we realize that the food supply operations at the university are reactive rather than predictive. The vendors do not have a system that helps them to predict how much to prepare on given days, but rather, let me say the eggs are about to get done. They'll react to that situation and order more eggs. Yeah. Then significant demand supply mismatch exists. Of course, we have talked about that. And vendors sometimes prepare much more food and they do not get the students to consume that food, which is also a problem. Now, also, demand exhibits strong temporal and weekday patterns. That means that our demand is the demand of the students within the university keeps changing. Yeah, it's not static. And we've realized that a smart ML-based forecasting system can significantly improve the efficiency of the food operators within the university. Then the limitations, the data set is limited to sampled vendors. Also, short data period may not capture seasonal variations and also macroeconomic events and other social events. Then per capita normalization is not applied and the real time systems are not yet deployed, but they will be deployed in the later stages. Also, our data sets are synthetically generated. We shall have to solve the sim to real domain shift or sim to real gap between the simulated and the real world. Yeah. Thank you so much for listening.
So that is what we had from our group, which is group 17. Thank you so much for listening.